Good morning, everyone. We are doing heat transfer fundamentals today. I know this was a topic that many people said they wanted to learn more about, so we're doing it twice this week. If you didn't get it all today, you can join us again on Thursday and take feverish notes. I'm Sunday Perez, Corporate Marketing Manager. I'm sure many of you already know that. And then we have our illustrious instructor, Paul Campbell, who will be teaching this course today. We have probably about 45 minutes or so of class, and then we'll have the rest of the time to do Q&A and get into all of that. So Q&A, you can either use the Q&A button at the bottom of your screen. Looks like two little conversation bubbles in the Q&A, or you can use the chat function. I'm monitoring both. If you have any technical difficulties or anything like that, please feel free to use either of those. I'll be watching both. I'm going to turn off my camera because Wi-Fi is precious in this house. But I am on and I am watching, so don't worry about that. With that, I'm going to hand it over to Paul and let's get going.
Awesome. Yeah, thank you, Sunday. I'll do the same thing, not because my bandwidth is a problem, just because it bothers me to be on camera, but I will bring it back as we get to questions and answers at the end. So let's get rolling on heat transfer. It's very simple topics this morning. We just want to cover some fundamentals, make sure everybody's good on typical operation, and maybe some of the fine points. And with that, thank you for joining us this morning. Let's see if we can get going here. Now listen, if you came to learn about LMTD or GTTD or LTTD, probably the wrong class. We're not going to spend any time on this. You're welcome. Software does all this for us, so we're not going to waste any time on this bad boy. There's other heat transfer formulas that come into play, but again, software does all the calcs for us, so we're not going to waste a lot of time on this. If I wanted to put you to sleep, we'd go through lots of examples on hard math, but forget that. We got better things to do this morning. If you remember from our boiler class, we talked about BTUs into the system is equal to a constant at 500 times gallons a minute times delta T. And again, if you wondered where 500 comes from as a constant, it's simply the weight of water times 60. It gets our units to work themselves out and becomes a constant. If we're dealing with glycol, that number changes a little bit. It might drop to 490, it might raise to 510. Depends on the viscosity or specific gravity of glycol, but for the most part, this is a constant. Now, for heat transfer, the beautiful thing is the heat that we transfer on the hot side, or the heat that we take out of the hot side of our system, we have to transfer that same amount of heat or energy into the cold side of our system. That's how a heat exchanger works. We can have different flows and different delta T's, but the heat or the BTUs that we're taking out of the hot side has to transfer into the cold side. That's just how it works. Very simple, okay? We do the same thing on the air side. It's just a little bit different with, you're dealing with CFM and delta T and a constant of 1.08. But we're gonna be talking about the wet side here. So let's get rolling on that. Now, I hate dealing with bullet points, and I'm not gonna read these through. We're going to be dealing with heat exchangers on the commercial side of the business, and that typically involves some type of shell and tube, or a plate and frame, or a braze plate. And we're going to talk about those and the differences between them. All right. So let's get rolling. We're going to start talking about a shell and tube, which is kind of old school on heat exchangers, but you'll still see them out there. And then more commonly, we're seeing a big switch or move going into plate and frames or some type of braze plate. And understanding the differences between the three and why we might select one versus the other. Okay, so that's our goal this morning. Now let me launch a poll. Let's see if I can get this going. Okay, now this is going to apply to our next little Our next little slide here. Okay, now this one's really complicated. So if you've got coffee or tea, or you're working on a bagel, whatever you've got in your hand, hang on for just a second while we talk this one through. We've got something we call a shell, which is where we, and then inside the shell, we've got something we call tubes. Okay, so this makes up our shell and tube heat exchanger. Very complicated. So I hope everybody's okay and they understand that one, but that's all we're doing with a shell and tube heat exchanger. We have some type of external shell, which is where we typically run our heating source. And then we've got tubes that are transferring that heat. So they're typically 3/4 copper. Normally you come in down low with your coldest fluid, you circulate it through your tubes, and it leaves warm nearest the source. Okay, so that's all we're doing with this guy. It's a shell and tube heat exchanger. Now, I'll get to my poll in just a minute. Let's talk about some advantages or features as it relates to this particular style heat exchanger. It does have a replaceable tube bundle. So if for some reason it fails or ruptures, or you end up with some devastating impacts or failures, you can replace it. You just have to make sure that you have enough room in front of this heat exchanger, adequate clearance, in order to pull this tube bundle. So if you've got a heat exchanger that's 4 feet long, you better have 4 feet in front of the heat exchanger in order to pull, or access, or service the tube bundle. Okay, that's pretty important. The other thing is you tend to have quite a bit of surface area on these. So if you have a tube that ruptures or fails, you'll see a lot of facility guys put a dowel in the tube that's affected. They'll put a dowel on both the incoming and leaving tube, and then they'll put it back into service. There's nothing wrong with doing that. And you'll typically dowel up a number of tubes until you start to notice a lack of performance or heat exchange. And in that case, it's probably time to replace the tube bundle. Now, let me end the poll real quick and we'll share results. Thank you everybody for taking part of this poll. The question is, what fluids are designed to run through this particular U-tube heat exchanger? Is this water to water, or is it steam to water, or no idea? So let's talk about it. Let me stop sharing. I'll just get it off my screen here for a second. So we had quite a few people say water to water, and you would think so. We certainly have water flowing through the tubes. So we come in down low with cold water, and we leave nearest the source with warmer water, and we send that out to our system. But if you look at what's happening on the shell side, you'll notice we have a very big connection on the top of the shell, and a very small connection at the bottom of the shell. So this particular unit is actually a steam to water setup. Steam changes volume roughly 1,700 times when it goes from a vapor to a liquid, or steam to condensate, and the connections here help to force that. So this is a good example of a steam to water heat exchanger, okay? Now, I know we don't do a lot of steam these days, so this might be a bit of a trick question if you're not used to seeing a steam application. Okay, thank you for participating in the poll. Majority of our shell and tubes are being served in a steam application. And all we're doing is we're controlling a steam control valve based on leaving water temperature. So we might be targeting 150 in, 180 out. And as we get close to 180, we're going to either open or close this valve based on how warm that water is heading out to our system. On the steam side, we have steam that comes in here as a vapor, but it leaves as a liquid or condensate as it changes state. We run that into a trap, and then out to our system, or back to our mechanical room. Let me see if I can launch my next poll. Bear with me a second. Oh, okay. Bear with me a second, because my next, I might be a little early on this. A couple things if you're using this for steam. There's always a vacuum breaker that gets installed in the field. And as steam condenses or cools, it pulls a vacuum. And this vacuum breaker simply opens up or reacts to the vacuum that's occurring in the shell and allows air to rush in. In doing that, it also allows our condensate to drain from our heat exchanger. So that's an important feature. You don't want to forget a vacuum breaker if you're in a steam application. If you want to tear up a shell and tube heat exchanger, this is how you do it. If you want to ruin it, it doesn't matter whether it's 4-inch in diameter or 30-inch in diameter, you start lifting condensate. And a lot of guys will assume that they can use the steam pressure here to raise condensate off their trap and get it up and over a doorway or an elevated return. You're going to cause a lot of water hammer damage in your heat exchanger. So we would not recommend this. You would always want your condensate going to some type of gravity drain. And if you have to lift it, it's a really good spot to put a little condensate return unit and pump it. Okay, but don't use the incoming steam pressure to lift condensate. Now we're going to do a steam class later in our series. We'll touch more on this, but just a quick example of why you don't want to lift condensate off of a shell and tube heat exchanger. Any heat exchanger for that matter. You'll tear it up. Yeah, forgive me, begin poll number 2. All right, I've already got poll number 2 going. Okay, so here's your question for poll number 2, and I'll give you just a minute to think about this. Now I'm changing it up on you. I went from a steam to water application to a water to water application. And you'll notice that the connection sizes are the same, entering and leaving on the shell side. And all we're doing here is we're taking hot boiler water and we're circulating it through what we call baffles. Okay, and those baffles direct the water flow around the tubes. So we come in hot and we leave a little colder. The question is, how hot can I get my leaving water temperature on my tube side? Okay, so I'm coming in on the boiler side at 180, I'm leaving at 160. How hot can I get this water? Now I'm going to go ahead and end my poll and we'll share results. I see it bouncing all over the place. So yeah, forgive me if I'm cutting you off. That's not the intent. But let's look at results. How hot can we get the leaving water temperature on the tube side of this heat exchanger? How warm can I get this thing if I'm coming in at 180? Well, with the shell and tube heat exchanger, the best I can do is get within 5 degrees of my leaving water temperature. Okay, so if I'm leaving at 160, the best I can do is get to 155. So whoever guessed that, congratulations, okay? Now, if you think about this, and by the way, thank you everybody for participating. I'm not picking on anybody, but if you think about this, this is not a great approach temperature. If we're coming in at 180, that's 25 degrees approach. Not a great number. So one of the reasons shell and tubes work very well for steam and not so much for water to water applications. Okay. So thank you for that. One thing to keep in mind with shell and tubes, there's no easy way to clean them. So if you end up with a lot of fouling or debris on the either on your steam side of the equation, meaning the outside of the tubes, or a lot of mineral buildup on the inside of the tubes, there's no easy way to clean or scrape that off of there. You could try running a brush down individual tubes. The challenge is when you get to that U-bend, it's hard to make it around. And external to the tubes, most people aren't removing their bundles to pressure wash or acid dip or whatever they want to do to remove scale and debris. So what we do when we're sizing a shell and tube heat exchanger is to add some fouling. And one way to think about fouling, it's just additional surface area or oversizing our heat exchanger. So when we do have scale on it, it still performs 5, 10, 15 years down the road, depending on how bad our fouling is. Most spec standards are 0005. And if you think about that, that's typically 20 to 30% additional surface area. We've seen 002. If you're doing work up in Nielsen in Alaska, you'll see 002 on their steam side because they have dirty steam. And that's anywhere from 80 to 110% additional surface area. So a lot more tubes or longer tube bundle to account for fouling or scale buildup on your tubes. Now for sizing, I'm not going to run you through any great detail here, but you can access this through B&G's site. Simply go down to selection tools, forgive me, and go to ESP Thermal. That gives you the same software that we use on the rep side. The only difference is it won't give you list price, it just gives you a price index to tell you cost ranking. Now, selection is very easy. I'm just going to run you through a quick example on a steam to water using 5-pound steam in this case. And on the water side, we're going to take 200 gallons a minute and heat it from 150 to 180. Spec standard or software standard is 0005 for fouling, and let's view results. You'll end up with a number of model numbers that are shown here, and then also some price indexes over here. Just to break down this model number, S means steam, U means U-tube. The first 2 digits here, in this case 10, means the diameter. So we've got a 10-inch diameter shell. The next number is the length. So this particular unit is 6 foot in length. And then the last one is number of passes, okay? Any model number that has a Q next to it just means there's something special about it. Kind of like me, there's something special about me, but you're not sure what it is yet. You might have some clues, but you're not sure. Same thing with this heat exchanger. There might be a different connection size, might be a flanged head, there might be something unusual about it. So all these are kind of factory standards, and then some are going to be quote special. Okay, you'll end up with a spec sheet and ultimately a drawing that shows you overall dimensions, clearances, things like that. One thing to be careful of, here we're showing a connection on the tube side of 4-inch NPT or 4-inch threaded connections. Software will let you generate these up through 8-inch threaded connections. I don't know a lot of people who want to thread 8-inch pipe. So you can opt for a flange connection if you like. The other thing to keep in mind, we try to limit our tube length or heat exchanger length to 8 foot or less, simply because we're asking for another 8 foot in front of this heat exchanger in order to service it. So if you're in a tight mechanical room, you may want to watch your overall length. Now just for fun, let's look at the effects of some fouling, okay? So I had 0005 on the tube side. Let's say we've got some dirty steam that's looking at 002 as our minimum. Software doesn't care where you put fouling. In this case, we've got a combined of 0025. That's quite a bit of a surface area. We run those same selections. You'll notice we went from an SU106 to an SU1012. So we went from a 6 foot length to a 12 foot length. That's not real practical. We're gonna increase our diameter and keep that at 7 foot length. We'll put some prices on that. You'll notice that we almost doubled our price by increasing our fouling factor. It's just a lot of excess surface area. And if you looked at the price of copper these days, that's not a cheap addition. You take that same unit and we add a flanged head to it, it just adds a little bit more money. And ultimately, you're ending up with some connections in the field that look like this. Flange connections on the head as well as on the shell. Okay? So kind of all things to pay attention to. If you happen to see a shell and tube come across your desk, or if you're out in the field, we can certainly help you. The other thing to keep in mind is when you're scheduling, or if you're scheduling a shell and tube heat exchanger, be very careful of your fouling factor. So we're seeing cold side, in this case, 001 on the cold side, and a fouling over here on the hot side of 0005. So you combine those two. That's 0015, okay? Here's another schedule where you've got 002 on the cold side and 002 on the hot side. Software combines those two, and total you're gonna have 004. That's off our charts as far as fouling factor goes. So we might be 250% total surface area. Drives you into some very large heat exchangers. So just be careful when you're scheduling. Make sure that your fouling factor is accurate because it has a big impact on how much surface you actually need. Okay, that was shell and tube. I didn't want to spend a lot of time there because I don't think we're going to see a lot of them. But if you see them in the field, we can do a rating on it or a performance to figure out how many BTUs it's rated for, or we can help you with some sizing if you get into it. Okay, let's change gears for a minute. Let's talk about plate and frames. Now, again, this is rocket science. We've got plates, typically a lot of plates that are sandwiched in what we call a frame. Okay, there's a front pressure plate and a rear pressure plate, and all that sits on a frame. So what you have is a plate and frame heat exchanger. Okay, very simple, made up of a lot of stainless or titanium plates, and again, sandwiched with kind of some very thick steel and rear pressure plates. Now, typically, plates are looking at 304 or 316. Sometimes you're into a pool application, maybe a saltwater pool or high chlorides, where you want to look at titanium. That's certainly an option. I want to say we're not building a space shuttle here, but it's typically the same cost as a double wall plate and frame. So kind of two plates. The other thing to keep in mind is your gasket materials. So our standard is a high temp nitrile, good to about 260 degree max temperature. If you're dealing with low pressure steam or higher temperature boiler water, you may want to look at going to some type of EPDM that gets you into the 300 degree range. Okay, we don't want to be close to our gasket life or max temperature. The greater buffer you have, the longer life you see out of your gaskets. Let's talk about how these work, because there can be some confusion on what's physically happening inside a plate and frame. So bear with me a second as we watch some animation. Basically, you've got hot fluid that's on every other plate or flows through every other plate, and sandwiched between that is the cold water. So you're kind of setting up some counterflow. Notice hot water is flowing down, cold water is flowing up, and it's sandwiched between, in this case, the cold water is sandwiched between two hot plates. Okay? So hopefully that helps as far as how that works internally to a plate and frame. Now let me go to my next poll real quick. Now this is very similar to the last poll that we looked at for approach temperatures, and same type of question. Okay, now we're coming in at 180 degrees, leaving at 160, just like our shell and tube. Question is, how warm can I get the leaving water temperature on my plate and frame? Okay, how hot can I get that water? So I'll give you just a minute. And I'm not very patient, so forgive me. But yeah, it's kind of fun to watch everybody chime in here. And I'll go ahead and end poll. Okay, so forgive me if I'm cutting you off. Again, that's not the intent. Let me share results, and we'll drag it over. How hot can we get the leaving water temperature on the cold side of the plate and frame? Now, obviously, answers are all over the place, and that's okay. That's why we're here this morning. The answer would be, sorry, I'm having a freaking out. Hopefully nobody's seeing that poll anymore. I think I downsized it. But the answer would be, a good rule of thumb is within 5 degrees of our entering water temperature, okay, not our leaving water temperature. So if you think about it, it's a 5-degree approach to 180 degrees. Okay, not the 155 we were seeing from our shell and tube, which is a 5-degree approach to our leaving water temperature, or 25-degree approach to our entering. So plate and frames are a lot more efficient at heat transfer and they can handle what we call a temperature cross, meaning that the outlet temperature here is warmer than the leaving water temperature on the boiler side, okay, or the hot side. That's a good thing. So if you're talking efficiencies or close approach temperatures, this is where plate and frame shine. Now, we have a lot of requests for close approach temperatures. Everybody gets excited by this. Hey, I'd love to get as close as possible to my entering water temperature. So I made up some conditions here, assumed 1,000 gallons a minute on each side, assume we're coming in at 120 degrees on the hot side of our system, and we want to get as close to that as possible with a 20-degree drop. Okay, so in this case, 1.5 degrees is my approach temperature, and I limited my pressure drop across the heat exchanger to 10 pounds. You might be able to raise that a little bit at 1,000, but I didn't want to go 1,000 gallons a minute, but I didn't want to go crazy on that. So we can do that, okay? A close approach temperature, 1.5 degrees, sets me up with a unit that's got 8-inch connections, but I need 424 plates. I need about 5,500 square feet of heating surface area to get there, and my budget's about $85,000. Now, what happens if I change that approach temperature? If I get away from that 1.5 and maybe spread it out just a bit, things change. So I did the same run, but all I did was say, hey, instead of 118.5, what if I go to 118, my leaving water temperature on the hot side, a 2-degree approach? Well, man, you'll see I can use the same unit, but I'm saving about 124 plates. I'm cutting my surface area by about 1,500 square feet, and my price just went down by about $20,000. Okay, I can do a 3-degree approach, and I'm almost cutting my surface area in half, and my budget went down, a good $30,000. Okay, so the point is you can do close approach temperatures, but there's definitely a cost involved with that. Normally when I'm asked to do it, I'll be like, yeah, I'll give you that 1-degree approach you're looking for, but I'm also going to give you a 2, 3, and a 5-degree approach temperature just for review. And next thing you know, an engineer comes back and says, hey, you know, that 5-degree approach is looking pretty good. It's about 1/3 of the cost of what I asked for originally. Okay, so just be aware of that when you're doing close approach temperatures. Yes, you can do it, but there's definitely a cost to it, simply because the amount of surface area required grows substantially. So feel free to lean on your rep a little bit. Make sure they're giving you accurate pricing, so you have good feedback. Now I wanted to look at a typical plate and frame submittal drawing, just for some quick review. One of the things to touch on is the fact that between your front pressure plate, which is fixed, and your rear pressure plate that slides, in between that are all your plates, okay, or your plate pack, as we call it. That's where all your heat transfer is occurring. You tighten these 2 plates, or at least this back plate, you tighten it to a dimension. You do not tighten these to a torque. If you start torquing down on this all thread and sandwich your plate super tight, what you're doing is you're flattening all your gaskets, and now they have no elasticity, and ultimately you're going to have to replace them. So just make sure that you're tightening the dimension here to the factory dimension or recommended dimension, not to a torque. The other thing to point out is a submittal is going to give you side 1 in and out and side 2 in and out. Software, or how do I say it? This dimension sheet doesn't care whether side 1 is hot or side 2 is cold. Okay, it doesn't care. Anytime we're doing software selections, hot is always on the left side and cold is always on the right side. That's just how software works. But in the field, you can alter your connections as needed. Just be careful that you follow the in and outs. So you can reverse them. You can get creative with this. You just have to make sure that you maintain a counter current flow. The last thing I wanted to highlight is down here, we're showing a plate quantity of 206 plates in this particular case, but the carry bar or the frame can hold 273 plates. That means I've got quite a bit of room back here for service or future expansion. That's a good thing. That makes my life easy. That's about 25% additional capacity. Okay. If my rear pressure plate is right up against the back of this frame, that makes life very difficult to service this plate pack. So most guys are looking for at least 10 to 15% additional room on this carry bar or their frame just to make service easy if they ever have to take it apart. So again, we can reverse flow if we need to. And again, feel free to lean on a rep if you want to come in down low and leave up top, or change connections. We can play with that. We just have to make sure that we are doing some counter current flow. It's a hard one to explain online, but you've got some flexibility in the field. You're not stuck with all left-hand connections for your hot side fluid. Okay. One thing that's really important that gets overlooked a lot, and that is max particle size, or how we're going to protect our plate and frame heat exchanger. You've got stainless steel plates that are sandwiched together, and they've got a certain distance between those two plates. A shell and tube has a 3/4 inch diameter tube that water is flowing through. You get a lot of particulates that just free flow through that, no problem. But a plate and frame, those plates are a lot closer together. And manufacturers are going to give you something called a max particle size. What size particle can I freely pass through my plate and frame heat exchanger? Well, if you have particles that are bigger than this, you got a problem. They're going to lodge in the heat exchanger. So the point to this is you want to make sure you're protecting your heat exchanger with a proper mesh size on your Y strainer or bag filter or whatever you're using to protect your system. If not, we have potential to clog our heat exchanger by dumping all the system debris into it. Okay, it's a great garbage can, but the way to protect it is to order a Y strainer with a proper mesh size. And obviously you'd want to be a little bit smaller than the max particle size. So make sure that's on your radar. We see a lot of installs where people are seeing a 50-pound pressure drop across their newly installed heat exchanger. Well, that means there's a lot of garbage in it. Same thing with braze plates. Okay, they're going to give you a mesh size or a max particle size, and it's just a matter of ordering a proper screen to protect it. A lot of guys rely on a suction diffuser or a standard Y strainer, and those might come with some pretty good sized perforations. And unfortunately, that's not protecting your heat exchanger. I'm going to, how do I want to say this? This might be a little lengthy example, but kind of an important one. And then we'll get wrapped up here pretty quickly. Last week or 2 weeks ago, we were talking about boilers specifically. You can take boilers and you can heat domestic hot water. You can't do it directly. Typically, you need some type of plate and frame involved, okay, which we might call an indirect style heat exchanger. And I just want to run you through a quick example if this is what we're going to do. If we're going to use our boiler water to heat domestic hot water, okay, or size a plate and frame to heat domestic hot water. First thing to keep in mind is if we're doing hot domestic, we typically want to add some type of liner. And factories can install stainless liners into our front pressure plate to keep us non-ferrous on the waterway. Okay, so we can go threaded, or if it's flanged, you can add liners so that our domestic water isn't contacting our steel pressure plate. A quick example. Let's say we're trying to heat 40 gallons a minute of water from 40 to 140. Okay, that's our domestic load. We've got 160-degree boiler water. BTU wise, we're just under 2 million BTUs, and we're sizing a heat exchanger that's double wall. So there's an air gap, which means we're not going, if there's a failure, we're not going to mix boiler water into our domestic. Okay, so in this case, we need about 79 square feet, 37 plates. Now we have to slow down for just a second. These are our conditions, but when are we going to get 40-degree water out of our domestic storage tank? Only on initial startup. Once that tank is up to 140, more realistically in the field, we're probably going to see 100-degree water coming out of that storage tank. And if we need to maintain a recovery of about 2 million BTUs, well, then we need to change our conditions a little bit. Okay, we're going to lock in our BTU requirement. We're going to increase our flow rate because our delta T is lower. And in doing so, we need a little bit more surface area. We went from 80 to about 144 square feet. Now, if we stayed with our original sizing with 37 plates and our lower flow rate of 40 gallons a minute, but we're only seeing 100 degree coming, well, we're seeing 100 degree come out of our storage tank, not 40 degrees. Guess what? Our recovery is well less than half of what we need to recover that domestic storage tank. What does this mean? It means we're giving people cold showers in the morning, and more than likely we're giving rooms away as part of that. Okay, so be careful if you're doing plate and frames for domestic storage tank. Make sure we're sizing it correctly for flow and delta T. That's really important. I stress it because we've seen it happen. Everything becomes a hot priority, and next thing you know, we've got UPS red on a lot of issues. Okay, let me launch my next poll. Let's talk about fouling factor with a plate and frame. This is a bit of a hot topic. Everybody who's used to sizing shell and tube is used to applying a fouling factor. It's just what you do. So when you go from a shell and tube into a plate and frame, you take that same mindset with you, and that is, let's apply a fouling factor. Let's talk about this. I just made up some conditions: 100 gallons a minute, 5-degree approach, 5-pound pressure drop with no fouling. Okay, so in this case, I need 43 plates, 225 square feet of heating surface area. And if I look at the details, my plate velocity at 100 gallons a minute and 43 plates is about 1.3 feet per second, meaning my water is flowing 1.3 feet per second across each plate. Okay, that's my velocity. If I add some fouling to this, oh, I'm sorry, I should launch my poll. that would help things. Wonder why there's no action on my screen. Now, if I add some fouling to this plate and frame, let's go with the spec standard at 0005, and let's see what effects that has. Well, I went from 227 square feet to 324. I increased my plate count by 44%. Okay, and when I add more plates, guess what? My velocity goes down. It went from 1.3 down to 0.83. Doesn't sound like a big deal, but if I have debris in my system, I want to keep it moving so that my plates kind of self-scour. If I slow my velocity down, I have more tendency for particulates to drop out, which means it's more prone to fouling. So it's kind of counterintuitive, but if you add a fouling factor, it makes your plates more prone to fouling. Okay, let me go ahead and end this poll and I'll share results. Should fouling factors be applied to a plate and frame? Yes, that's the only way to account for scale buildup. You would think so, and I agree with you on this, but there's another option here. Yes, just like YouTube, a fouling factor should always be used. Again, yes, you would think so. No, excess surface area is a better option. I'm going to agree with this one, and I'll show you why in just a minute. Okay. No, best to ignore it. Honestly, that's what we tend to do in-house. If we see fouling factor applied, we will tend to ignore it because it makes conditions worse. And sorry, no idea. No problem. Listen, this is why we're all here talking about it. So let's talk about another option besides fouling factor. Another way to do it is with software, you can add 5 to 10% excess surface area to your plate count. I think in our case, we went from 41 to 45 plates, a total here of 7% excess surface area, and yet our plate velocity stays high. Okay, that's a good thing. So watch out for fouling factor on a plate and frame. It can get you into a bit of trouble if you're not careful with it. If you're scheduling plate and frames, one thing to be careful of is your pressure drop. Most of the time, software is going to give you pressure drop in PSI. A lot of times we see that thrown on the schedule in feet of head. Big differences. Okay, so just be consistent on your units. If you're selecting, most plate and frames have a higher pressure drop, and we're going to list it in PSI, not feet ahead. Here's a good example of what can happen if you are making selections online without maybe talking to a rep or getting some price feedback. This one seems pretty simple. 1,000 gallons a minute, coming in at 60 degrees on the hot side, leaving at 57 on the cold side, so it's a 3-degree approach. 7-pound pressure drop on the hot side, only a 5-pound pressure drop on the cold side, and in this case, a double wall construction. This unit, this P188, is the largest heat exchanger that B&G makes. And with 450 plates, it carries a list price of $515,000 each. You've got 1.5 million sitting here with 3 heat exchangers. Now listen, we love to sell that. That's fantastic. Based on conditions and maybe changing some pressure drops, we could help cut this number a little bit. Also comes in at about 21,000 pounds. And height-wise was so tall that it needed a low boy to get from Buffalo into the port in Seattle. Okay, so just be careful if you're making selections online. Make sure you're doing some price research as well. Otherwise, you could end up with some very expensive heat exchangers. Okay, I'm going to launch my last poll here, class survey. We're getting close to the end. Bear with me a second. One thing you'll see with plate and frames, most manufacturers are under AHRI. AHRI is very important as far as maintaining accuracy on printouts or selection or software, so that anything we enter into as far as a condition is also going to hold up in the field. That there's no games being played, that how do I say it? That we're guaranteeing performance in the field based on the printout that comes through in a submittal process. So AHRI has certain criteria that that they are chasing glycols up through 50%, water or seawater applications, flow rates up to 20,000 gallons a minute, and BTU loads at 240 million or less. So AHRI is very active on the heat exchanger side of the equation, just to make sure they're protecting owners and engineers with guaranteed performance in the field. Okay, last little section, and that's on braze plates. The big difference between a plate and frame and braze plate is you'll notice the plates look very similar. Okay, they're just corrugated stainless. The difference is they're all sandwiched together and then they're brazed at the factory, either with copper or nickel, depending on your application. So it's a sealed unit. Advantage is you can run much higher pressures, up to 435 pounds of pressure, temperatures up to 450 degrees. Okay, all that is good. You're also seeing some very large port connections here. as small as 1/2 inch, but all the way up through 3, 4, sometimes 6-inch connections. You can get some very pricey braze plate heat exchanger selections. An advantage of a braze plate is you don't need room to service it. You can put it up in your piping, you can get it off the floor. But if you're into some large port connections, you may want to consider a plate and frame as an alternate, simply because you could be talking about a $35,000 to $50,000 heat exchanger. Sometimes it might be worth justifying the floor space. But again, no service required here. Just make sure that you're protecting the heat exchanger, because if it fouls or plugs with debris, there's no easy way to open or service it. Okay, so that's where that max particle size really comes into play. You can also do this with refrigerant, light oil. There's a number of OEM applications going on. But yeah, a braze plate, certainly a lot of activity there. And with no gaskets required, a lot of, I would say it opens up a lot of interesting applications. Okay, where are we at? Time-wise, we're at 10:40. I ran a little long. I apologize for that. We're sitting about 10:50. Sunday, if there's any questions, now's certainly a good time.
Yeah, we have a few.
Okay, great.
Which gasket works best for high levels of silica?
Oh, yikes. Really good question. I don't know. I can get in touch with the factory and find out. That's a great follow-up question. I don't want to mislead you there. Most of our systems in the commercial world are very clean, but we do see geothermal, and we do see some pool type applications. But yeah, let me get back to you on that one. I don't have an answer for you.
Sean,
good question.
To you. I have your information, so I'll get that over to Paul and we'll follow up.
Yeah, perfect.
Okay, next question. How do you select the PSI drop for a heat exchanger?
Oh yeah, good question. With a shell and tube, you really don't have to worry about it. Typically, you're looking at 5 to 10 feet max, and usually it's coming in less than that. On a plate and frame, you may get codes that require you at 8 to 10 pounds, but really your impact is on the pump that's getting selected, and ultimately horsepower, based on how much allowable pressure drop you can accommodate. We've seen some very conservative selections where you're 5 to 6 feet of head, so you're talking about 2 pounds. We also see them come in at 10 to 15 pounds max pressure drop. So it really depends on your application and what you're willing to invest in pump horsepower and how it affects your system. I don't have an easy answer for you, other than the limiting factor on a plate and frame is typically approach temperature and pressure drop. And a lot of times you just have to play with one or the other to find which one is limiting you as far as plate count or ultimately cost. But yeah, very good question.
I was going to say, you're welcome, Kimmy. I'm glad you learned a lot from the class. We appreciate that feedback. Okay, one more question I have right here. Alternative to using fouling factor, increasing effective surface area.
Yes, that's a true statement. So you can certainly, fouling factor, I don't want to say that. Fouling factor can be a variable. So depending on how many plates you've got or your total surface area, it's going to multiply out, where using excess surface area, well, it kind of has the same effect. So fouling factor is based more on tube velocity or plate velocity, and excess surface area is based total on your square foot of surface that's required for the duty. So to me, surface area, and when you talk to the factory, they say, hey, excess surface area is the way to go, simply because it eliminates the variable, which is your internal velocity. So I know that's not a great answer, but excess surface area, if you know you'd be comfortable at 5, 10, 15%, that's an easy one to plug into software, versus fouling factor, which is more of a variable based on your plate velocity. I hope that makes sense. It's a good question, and probably not the best answer.
And just chat us if you need more information or want us to follow up with you to discuss further. Okay, one more question just came in.
Sure.
Can you get extra heat transfer by increasing flow rate on one side of the heat exchanger?
You can. And yes, you have to be, it's a tricky one. We see a lot of conditions where it's summer, winter conditions, and you always have to pick the worst case and look at your total surface area. And then we can do a performance for your worst case load. But we never know whether it's summer or winter, which is driving your total plate count or surface area. Can you get more performance? You can. You have to be careful. If you're running more flow across your heat exchanger, you also see a higher pressure drop. So you might reach a limiting factor there, depending on your plate count and your overall system design, and what ultimately what your pump is capable of. But yes, if we can help evaluate your heat exchanger, we do that all the time. Happy to do it. Look at various conditions, various flows, approach temperatures. We also have the ability, if it's an existing heat exchanger, we can go in and do a rating on it. So we're basically looking at your plate count and look at various conditions as it relates to those plates that are installed in the field. Take some of the variable out of it. Okay, but yeah, good questions.
Andy, feel free to follow up with us if you want to discuss that further. Our emails are on the screen right now, pcampbell@chchydro.com and sperez@chchydro.com. As Paul said, we're happy to discuss it further with you and review your case study that you're looking at. Okay, a couple more came in.
Okay.
Best method and or chemical for cleaning scaled plates.
Ooh, that's a really good one. A lot of guys are just going to take it apart and pressure wash it. Obviously labor intensive. You also have an option to do a backwash feature. That's simply a valved assembly that is going to do it either based on time or pressure drop to reverse flow through your heat exchanger with the intent to clean it or flush it. Chemicals gets tricky, and that's certainly not my strength. If your chemicals aren't a good balance, you may be attacking your gaskets. Honestly, if your gaskets fail or they have to be replaced, if you're replacing the whole gasket set, a lot of times it's cheaper just to buy a new heat exchanger, unfortunately. So yeah, be very careful with the chemical approach, and I'd be talking to your chemical supplier if that's the case, and confirming your gasket material, and maybe make sure you get some guarantees before chemicals hit that heat exchanger. Not a great answer, but yeah, good questions. There's various options for you, and we can certainly help review those if you like. We've got some details on backflush and other things.
Okay, John, again, feel free to reach out to us if you'd like more information.
Yeah, certainly.
Okay. Tim Balti, big danger of overflow is increasing the temp drop to your heat source, which may cause condensing, etc. That might have been in reference to.
Yeah, that's good. Yeah, obviously everything has an impact. So yeah, Tim's got a valid point.
Okay.
Yeah.
Then we have one more question that just came in. Do heat exchangers have minimum flow rates?
Oh, yeah. Yes, they do. Now that's a really good question. So a lot of it comes down to a Reynolds number, which we have to use software to figure that out, but software will give us a Reynolds number. If you're looking at a shell and tube, a good rule of thumb there is a Reynolds of 2000 or greater. So a lot of times we'll do the same thing. We'll lock in the heat exchanger, and then we'll look at reducing flows until we get to a Reynolds that's down around 2000, and that's kind of our minimum flow rate. A plate and frame, the Reynolds is about 150. So we'll do the same thing. We'll lock in our plate counts and drive that flow rate down until we get near a Reynolds about 150. Not so much based on pressure drop. We used to do it based on pressure drop, but finding out the Reynolds is a lot more accurate. Yeah, really good question. It certainly I don't say it specific based on various on the application or your conditions, but yeah, we can certainly help figure out minimum flows. If you drop too low on flow rate, I don't want to say it, flows become laminar, and with laminar flow, you get no heat transfer, so or limited heat transfer. So yeah, it wouldn't be very effective at that point. But yeah, great question.
Okay. That was our last question. Are there any other questions? We have 5 more minutes that we can take up to answer anything else.
Sunday, I do have two slides to share if I can do that real quick.
You have the time.
Let's, if anybody's interested, I just have a couple pictures of a typical heat exchangers that might ship from the factory, showing that your pressure plates, obviously the front one has all your system connections on it. Here's that back pressure plate with some long all thread, and then a carry bar. Now, this gets a little crowded, so forgive me, but if you look at the back, you'll notice that, wow, we got a lot of room for expansion back here. Very easy to service. If your heat exchanger is a little shorter, it might ship face down. And here you're looking at, obviously, a plate pack, and then the carry bar that's standing in the air. So obviously, again, room for service, extended on the all thread, okay, but make sure you don't fork under here and cause some problems with any of your studs sticking out of that front pressure plate. So just be careful how you lift it. The other thing to point out, you'll notice that you don't see any plates. So there is a galvanized or a stainless shroud that covers the plates. So if there's a gasket failure, you don't walk by and get hit with boiler water or some chemical laden water. It all gets directed down towards the floor. So this is open, but if you have a gasket failure, you're going to expect to see some puddles down below here, not get hit hitting the side of the face. Okay, I hope that helps everybody as far as typical installs or shipping methods.
All right.
Okay, great.
All right, well, if there are no other questions, thank you for joining us today, this morning. If something pops up as we exit this class, feel free to email either one of us and we'll get you the answer or direct you to the person who can. We're always here to help you with whatever questions or problems you're coming up against with your projects. So feel free to use us as your resource. Thanks again, and we look forward to seeing you in the next class.
Thank you, Sunday. Thanks, everybody.